Okay guys, so here's your quick, hopefully quick explanation of section 2.4, which is when we're dealing with permutations, but we have objects that are identical. This one, I'm hoping, is fairly straightforward. It's not a lot different than the permutation stuff you've been working on already. It's just now we have to worry about what happens when there's things that look exactly the same and how that changes our final answer. So the example we're going to start with is this one of coffee mugs. We want to line up 4 coffee mugs on a shelf. We've got 2 white, 1 red, 1 blue. And it says how many different ways can we line them up? For right now, let's say one of the white mugs has a chip in it so we can actually tell the difference between the two. And then we're going to draw out the possibilities. So the one that's white, I call W, red is R, blue is B, and then for the one that has a chip in it, I just did WC, so white with a chip. So that we can see the different numbers. So if you draw it all out, you can start with the white one, have white with a chip next, then alternate your red and blue. You could put white, then blue, alternate your red and the white with the chip. White then red, alternate your blue and the white with the chip. If you do this kind of systematically, so I started with all the whites, then I started with all the whites with the chip, then I started with all the reds, then all the blues. You get 24 different lines we could make, or rows of mugs we could make. This is the same thing as we have 4 positions we need to fill. We've got 4 different mugs for the first, 3 for the second, 2 times for the third, and then whatever's left over for our end. That's also going to give us 24. Okay, but if we can tell the difference between the 2 white mugs, we have 24 different ways we could line them up. This is now what this section is talking about right here. So, what if there is no chip in that white mug? What if we can't tell the difference between the 2 white ones? When that happens, when we lay out our exact same 24, so all I did was recopy the ones above down here, but instead of WC, I just put W. Now we have versions that are identical. So if I look, I have WWRB and WWRB. Those are exactly the same. And if I lined them up this way, or I lined them up this way, I wouldn't be able to tell the difference. So I can't count these twice. This second one doesn't count for anything because it's exactly the same as the first one. We've got WWBR, WWBR, they're exactly the same. We've got WBRW, WBRW. So one of them has to be crossed off. WBWR is here. WRBW, WRWB. So those 6 right here were just identical to those first 6. When I look in my, starting with my red, this RBWW is the same as RBWW, so I can only count it once. This one is the same as this bottom one, so I can only count it once. These 2 are identical, I can only count it once. I'm going to do the same thing for all of these. I'm going to cross off anytime I've got a double, and I'm going to count up how many I actually have now. So there's 6, 7, 8, 9, 10, 11, 12 in this case. So when I was able to tell the difference between the 2 white mugs, I had 24 ways I could line them up. Once those 2 white ones are identical, I only have 12 different ways of putting them in a line. So the point is, once we can tell the difference between the white ones, we have permutations that are identical, and since they're identical, we can only count them once. This means there will be less permutations possible if the objects within our set are identical. Okay, this is the key takeaway here. As soon as you have things that are identical, you're going to end up with less possible lines of them or different permutations of them than when you have all identical objects. Okay, so we don't always have to draw out all of those possibilities like we did on that first page. There's a formula that we can use to solve these problems, and this is it. So the number of permutations possible is equal to n factorial over a factorial times b factorial times c factorial. So the number of permutations equals the total number of objects in the set as a factorial on top. And then on the bottom, you're putting the number of objects that are identical. So if you only had 2 different colors, you'd just do a factorial, b factorial. If you had 10 different colors, you could possibly have 10 things on the bottom. You just use as many or as few letters as you actually need. This formula is not on your formula sheet. It is something you need to memorize or remember. So in order to use this formula, we're going to get the same answer, hopefully. But the mugs question, we had 4 mugs in total, 2 white, 1 red, 1 blue. So when we use this new formula for when permutations when objects are identical, we had 4 mugs in total, so the 4 goes on top of the factorial. On the bottom, we would have 2 factorial because there's 2 white mugs, 1 factorial because there's 1 red, 1 factorial because there's 1 blue. So we'd end up with 4 factorial over 2 factorial. This is going to equal 12. So it equals the same thing in the end. The simplification for this is that you don't need to include anything you only have 1 of, because 1 factorial is just equal to 1. So the red and the blue didn't technically need to be in there, because 1 factorial is going to be 1, and when you multiply anything by 1, it doesn't change. So we only have to put in on the bottom the things that are actually repeated. I just wanted to show you how we would fill it all out so that you know what goes down there. Okay, so if we try this one, it says you have to hang 9 shirts up on a clothesline. You've got 1 green, 1 yellow, 2 white, 3 blue, 2 red. How many different arrangements are possible? So P is going to equal n factorial over a factorial, b factorial, c factorial, where n is always the total number of things that we're lining up or whatever we're doing with them. So in this case, that's going to be 9. So we're going to have 9 factorial over... on the bottom, we need to put anything that's identical. So we've got 1 green, so we don't have to include 1s. We've got 1 yellow, we don't put that one in. We've got 2 white, so we'll put 2 factorial for the whites. We've got 3 blue, so we'll do 3 factorial for the blue. We've got 2 red, so 2 factorial for the red. How many different arrangements are possible? So we're going to do 9 factorial divided by 2 factorial times 3 factorial times 2 factorial. When you do this in your calculator, you're either going to want to do it in steps or you're going to want to put brackets. So you're going to do 9 factorial divided by, and then a bracket, 2 factorial times 3 factorial times 2 factorial. And we get that there is 15,120. If you don't put the brackets in there, you're going to put the totally different answer. Because what this does is it does the 9 divided by the 2, then it treats the 3 and the 2 after that as if they were up on top of the fraction. So make sure you put brackets in. Okay, so there's 15,120 different arrangements. Okay, we can also use this formula to help us solve conditional problems, depending on what the conditional problem is. In this case, it says how many ways can the letters of the word Canada be arranged if the first letter must be an N and the last letter must be a C. Canada has 6 letters. So we've got 6 positions to fill. The conditions are this first letter has to be an N and the last letter has to be a C. There's only 1 C in Canada, so there's only 1 possibility for that last letter. There's only 1 N in Canada, so there's only 1 possibility for that first one. What that means is this middle piece, those 4 have to be the letters A, D, and A. But the A's are all 3 identical. So this isn't just 4 times 3 times 2 times 1, because if we put A number 1 in, A number 2 in, a number 3 in and then the D, or we put 3, 2, 1 and then the D, they're going to look exactly the same because the A's are all identical. So in order to figure out this middle piece, what we're going to do is we're going to say that there's 4 things we're going to choose from, and we're going to use our repeat. So n factorial over a factorial, b factorial, c factorial, in order to figure out how many possibilities there would be for those middle ones if we have to ignore the repeated letters. So this is going to be 4 factorial over, there's 3 A's and technically 1 D, although we don't have to put the 1 in there. So 3 factorial, or 4 factorial, sorry, over 3 factorial is going to just equal 4. So what that means is when we have to do an N for our first letter, however many possible arrangements there are for the middle, and a 1 at the end, our total is going to be that there's 1 possibility for the first letter, and we need the 4 possible arrangements for the middle letters, and we need the 1 for the C at the end. That tells us there's going to be 4 possible arrangements of these letters in total that look different. Because there's only 4, I'm going to draw them out just so you can see what those 4 would look like. So we would have the N first, A, D, C. We can have N, A, D, A, C. So those 4 right there. Anything else is just going to be a repeat of one of those 4. Okay, so we found our outside pieces because those were our conditions, and then we use this permutations when we have identical objects to find the total arrangements for those middle letters, and then we had to multiply all those together because we needed the entire arrangement of 6. So this piece and the middle piece and that last letter. Okay, the other thing we can do is problems where there's like roots or paths. Okay, these commonly come up. Actually, I like solving them, so there probably will be one, at least one on your test. So in this case it says Julie's home is 3 blocks north and 5 blocks west of her school. How many routes can she take from home to school if she always travels either south or east? So first of all, you have to know your directions. North, east, south, west. Line them up typically this way so that you know which direction she can go. She's going from home to school, and it's told us that they're 5 blocks west from school. So 5 blocks west, 3 blocks north to get home. So all we do is we draw a 5 by 3 grid. We label the 2 pieces, or the 2 starting and ending points. And then it says she wants to, how many ways can she go from home to school if she always travels east or south? So we're starting at her home. What we have to do is we have to figure out how many ways there are for her to get to each intersection, all the way across until we get to the school. If she's starting at home and wants to get to this point right here, there's one way she can get there. She can walk straight east. It said she's only going south or east, so it's not like she could go south, east, then north and get here as well, because she can't go back north. So if she wants to get to this point right here, there's only one way to get there. She can walk straight east. If she wants to walk to this point, there's also one way to get there. She can walk 2 blocks straight east. There's only one path that takes her to that point on our grid. There's only one path that'll take her to any of these. All she can do to get to any of these outside edges is walk straight east. So there's one path that gets her here, there's one path that gets her to this last. Same with going down. If all she can do is go east or south, there's one way she can get to this intersection. She can go straight south from her house and that's it. There's no curving around and coming back to it. Here there'd be one, there'd be one. If she wants to get here though, there's two paths. She can go east, then south, or she can go south, then east. So there's two ways to get here. To get right here, there's going to be three ways. She could go all the way east, then south. She could go south and then all the way east. Or she could go east, south, east, and get to right here. If she wants to get right here, there's also going to be three ways. She could go east 2 blocks south. She could go 2 blocks south, then east. Or she could go 1 block south, 1 block east, 1 block south. There's a pattern here. You don't actually have to draw out all the paths for all the different ways of getting to these places. The pattern is if you take your corners and add them together, they're going to equal the diagonal part. So if you're looking at for this one right here, if you take this one and add them together, they're going to equal 2. If you take this one and this 2 and add them together, they're going to equal 3. If you take this 3 and this one and add them together right here, you're going to get 4. This 4 and this one will add together to give you 5 right there. And then the 5 and 1 will add together to give you 6. And you're going to do that all the way across. So you've got 1 and 3, which will add together to be 4. 3 and 3 are going to add together to be 6. 6 and 4 is going to be 10. 10 and 5 is going to be 15. 15 and 6 is 21. 6 and 4 gives you 10 down here. 10 and 10 is 20. 20 and 15 is 35. 35 and 21 is going to give you 56. So there's 56 ways to get to school. Okay, so the key ideas for doing these is once you draw it, or if you're given one already, from your starting place, in the direction you can go, everything is a 1 along the outside edges in those directions that you can actually walk. And then you're adding up your 2 diagonals to get your, or your 2 corners, I guess, to get your third corner of it. So the 2 diagonals equal that last one. This one's a pretty straightforward one where you're just given a rectangle and you're figuring out the paths. What they can also do to you is give you something that looks like this. There's 2 different ways you can do a question like this where there's pinching off points. So if you're trying to get from A to B, one way is to do it like what we just did. So in this case, we're going to say you can go north or west. So if you're starting at A, you would have 1s along the outside edge, 1s along the bottom, which makes this a 2, 3, 4. When you fill them all in, you end up with a 20 at this completely pinched off point. If you come to a point that looks like that, where there's no, it completely kind of stops and then you're starting a new section, whatever number you've got right here carries on. So this would be a 20, that would be a 20. So we went up and out with our number. Those 2 20s are going to add together to make 40. That's going to give us this pinching off point. This 40 now is going to carry on all the way up. And now these 2 corners, 40 and 40, are going to equal 80. Those 2 are going to be 120. Those 2 are going to be 120. And that last one is going to be 240. So there would be 240 ways to get from A to B. The other way you can think about this, if you don't actually like this, is when you have these pinching off points, you can think of them as 3 separate sections. So I'm going to call this one down here section 1, 2, and 3 because we're going from A to B. For section 1, our 1s are still going all the way out. Section 1 is actually not going to look any different than it did originally. So there's 20 ways to get from A to this first pinch off point. If we think of this next piece as its own section, we're going to have 1s starting off. 1 and 1 is going to add to 2. So we've got 2. There's 2 ways to get through section number 2. And if we think of section 3 as its own thing, we've got 1s along the outside. We're going to add them together. So there's 6 ways to get through section 3. And if we think of them as 3 separate things, we have to do section 1, and we have to go through section 2, and we have to go through section 3 in order to get from A to B. So there was 20 ways to do 1, there was 2 ways to do 2, and there were 6 ways to get through section 3. And if we do 20 times 2 times 6, we're still going to get 240. So you can think of it as all one thing, or you can think of it as separate sections, and then you're going to multiply them together in the end. Okay, that's only true though if you have those pinching off points that completely stop. Anything else, you're going to drag your numbers forward. Okay, give these a try. The paths tend to be confusing until you kind of see the pattern of them. So don't worry if at first I'm not making sense. We'll go through it. All right, good luck.